Hello. You should really hear me. You should see the desktop now. Is everything say okay?
Yep.
Okay. Okay. I got everything ready. Okay. What we're going to do today is we're going to talk some more about grammars. I think probably today we'll finish the grammars. If not today, then on next Tuesday. So we're going to look at finish section finish this ideas in chapter 3. I put a reading assignment in here for you to start reading chapter 5. And chapter 5 is an introduction to this language called ML. Okay, so we're going to start looking at a new kind of programming language, a functional programming language called ML. It's an older functional programming language, but it's still a real important one. ML here doesn't stand for machine learning. In fact, ML stands for meta language. Okay, it's a language it's the language behind Microsoft's F sharp. Essentially, F sharp is just the dialect of this language ML, and it's still one of the more important functional programming languages around. It's one of the most influential functional programming languages ever. So we're going to learn a little bit about ML programming. So start reading chapter 5, and we're going to use ML as a motivation for a lot of ideas in programming languages. Uh, if you look at what's happening in the Java programming language and the C++ programming language and the JavaScript programming language, you look at all the changes that are happening in those languages, they almost all come from ML. Yeah, the ML language is becoming the language that has been motivating a lot of the changes in the languages we make much more use of. So learning ML is a good way to understand how Java is changing, how C# is changing, C++ is changing, JavaScript, all these languages, Python included. They're getting closer and closer to being more like ML.
Can you bring all that money?
Hello?
You might have to go to the bank after we put my
Okay. Okay. Um, okay. So start reading about ML is very different. It's a very different kind of language than what you're used to. So it's a real it's good for the study ML is good for two reasons. One, it's the basis for a lot of the changes that are happening in modern languages like Java and C# and C++. And also it just makes you learn to think a little bit differently. Learning to think in a language like ML is going to make you think differently about programming. Functional programming languages you don't quite use them the same way you use what we call imperative programming languages like Java and C++ and Python. Okay. All right. So, and then you'll need a version of the programming language. And here's a link to an installer that you can use. It's not very big. It's not a huge language. If you install Visual Studio, you download gigabytes worth of stuff. If you download this, the installer is all of
So it's just a compiler, not like a full IDE.
no, well, it's neither. It's a
Interpreter or
yes, yeah. It's an interpreted language, so it's not an IDE. It's a compiler and an interpreter, but not an IDE. Okay, and we'll practice with it next week. So and there is a kind of an IDE, a little bit of an IDE that can go with it. We'll add to it later on. Okay, so we'll start with this one, and then we'll see how to use it, and then we'll see how you can no, we'll see how I'll show you different things you can do with it. Okay, all right. So, but right now we want to go back, and I'm going to just delete that for now. I'm not going to install it. Okay, we're going to go back and look at more examples of grammars. Okay, now I'm going to get an example. Let me see. Okay, here are okay. here are the grammars we started with. That we did G1, G2, G3, and G4. We were playing around with these in class the other day. Today we're going to start looking at G5. And this is the version that we looked at the other day, and I've got another version on my desktop because in the book there was a modified version of G5, so I've added that to this list. So I'll put this one up on the website after class. So we're going to look today at what G5 does for us and what this modified G5 does, and then we'll look at G6. Okay, and remember, we're trying to build up a grammar for arithmetic. Okay, so we're trying to build up a grammar for arithmetic, and what we need to worry about are two things. If somebody gives us x plus y plus z, or say x minus y plus z, what order do we do things in? How do we know what order is the right way to do things? Because, for example, here, it matters if we do this subtraction first and then this addition second. Here, because of addition, it doesn't matter if we do this one first or this one first. It doesn't matter. But with subtraction, it does matter. And similarly, if I do x divided by y minus z, it matters a lot whether I do the division first or the subtraction first. Okay, what order should we do the operations in? Okay, now you were taught rules in school, but programming languages need the rules built into them. Programming languages don't just sort of remember these rules. What do you do to a programming language to say, do this from left to right, do this one from left to right, but do this one where division comes before subtraction? So if I did it like this, then you would do the division first, then the subtraction, okay? And if I added another term here, you would still do that division first, then you do that subtraction, then you do the addition last, okay? Right. So how do programming languages get these rules? And the answer is through their grammars. It's the grammar which tells the programming language how to build the parse tree. And it's the parse tree, so for example, if I build parse trees for these from top to bottom, the top one's parse tree is the sum of x, okay, the sum of x with the sum of y and z. So I want that expression to give me that parse tree. Okay, that parse tree then said, no, I did that wrong. Yeah, that's what I did that one from right to left. I wasn't thinking I did that one wrong. So this one should be over here. Okay. And that would be x plus y. And then after you added x, y, then you can add in the z. So I want this one to have that parse tree, which then does that sum first, okay? And similarly, the next one should have a real similar parse tree. The next one should just put a subtraction in there. So you do x minus y first, then add on z, okay? If we did like this one here, okay, this one we're supposed to do that division first, okay? So the parse tree, we want the parse tree, we have to write the grammar to force these parse trees. We know what the parse tree, we know how we're supposed to do these. We know that we should do the division first and the subtraction second. So that means this is a subtraction tree of x on the left. It's a subtraction of x with a division of, oh, now it's going to be confusing, I'll put the division like this because otherwise it's confusing with the thing I'm using for the building the tree. So it's a division of, well, actually, the other slash. It's a division of Y and Z. Okay, so that parse tree reflects what we mean by that. And then this one would be a subtraction. Oh, well, no, the last thing you do is this one. So that's at the top of the tree. So for that one, you'd be doing a sum. Okay, you'd be doing a sum of something on its left and something on its right. On the right of the sum is a Z. Okay, what's on the left of the sum? On the left of the sum is this thing, but that's a subtraction of two things. That's a subtraction of, okay, so this is a subtraction of two things. It's got X on its left, and on its right, it's got the division of two things. Okay, and it's finally the division of Y and Z. Okay, so we want the grammar to somehow force these parses on us, that we would see we would get these kind of trees from the grammar. Okay, so programming languages need grammars to tell them what to do. Okay, and that's what we want to do over here. We want these grammars are going to help us. These grammars are written so that when the programming language applies its parser to the grammar, it gets the correct trees. And then these trees do the order of, since you evaluate the trees from the bottom up, then you do the order evaluations correctly. Okay, so this was supposed to have been added first, but that's lower in the tree. You have to do this addition before you can do that one, because you don't have a left-hand side for this one. So you can't do that addition until after this one's been done. So you do that addition, then this one. So that did this one, then this one. And then this tree just put a subtraction over here, because since subtraction and addition are the same level of precedence, you do them from left to right. Okay, so you don't do subtraction first or addition first, you do them in left to right order, just like here when you did these additions from left to right. Okay, then over here, now a division has higher precedence than a subtraction, so this should be done first. So that puts it lower in the tree. Okay, so the tree, it's a subtraction tree of X with this result. Okay, and then here, the subtraction and the addition, this is done first here. So it's at the lowest part of the tree. Okay, but then out of the subtraction and the addition, they should be done from left to right. So this subtraction, let's see, did I do that right? Yeah, this subtraction should be done first because it's on the left. So it's lower in the tree. And it's the addition that's done last because we're doing from left. The addition and subtraction are done from left to right. It's as if they were, make it easier to read, you put parentheses there. So it's this minus this. So it's like this one here where the middle result, see, the middle result was over here. See, now the middle result's right there, same place. Where that Y was in that tree is where this thing is in its tree. See, it's in the exact same place. Okay, so it's playing the same role in the tree. Okay, so the grammar should give us these trees. So we have to figure out how to write the grammars so that they, let me save that. We have to figure out how to write the grammars so that the grammars build the trees this way. Okay, now we played around with these grammars the other day. Okay, now let's think about what these, if we looked at these three, the book took them as a simple example, but actually, if you go back and look at these carefully, almost all the ideas you need to understand are buried in this example. So let's see how let's go back and redo these three examples and look at them slightly differently. And we see that there's something really interesting going on here that explains how things work. Okay, so I want to use those examples. I'm going to open another window. Okay. Okay, work in another window. So I can keep work in this window with some and then use the grammar over here to understand it. Okay, so we have something like A minus B minus C. Okay, we want to parse that. We want to know how we should parse that using this grammar. This grammar says that, okay, the idea is that the key idea is this recursion. See how we're saying what a subexpression is? And on the right, we're saying, well, a subexpression includes a subexpression. The key idea is to see that there's recursion here. A subexpression is made up of subexpressions. Now, sub here means subtraction. So it's not, this is a subtraction expression is made up of subtraction expression minus subtraction expression. Okay, and that makes sense because what can I put on the left and right hand side of a subtraction? Well, I can put numbers, but I can also put the subtraction of things. See, it makes sense to put the subtraction of things on the left and right hand side of a subtraction. So a subtraction thing is a minus sign with subtraction things on each side. Okay, so see over here, I can take the 3 and replace it by 5 minus 2. I'm putting the parentheses in there just to make it easier to read. Yeah, according to them, yeah, I could write it like that too. But the idea is that a subtraction thing has, nothing stopping me from putting subtraction things on either side of the minus sign. So there's recursion there. A subtraction expression is a minus sign with subtraction expressions on either side. Okay. Over here, notice that in this version G2, there's less recursion. See here, the recursion here is on the left and the right. Over here, a subtraction expression they're saying is a minus sign, not with anything on the left, only a variable on the left, and then a subtraction expression on the right. Okay, so when you switch from grammar 1 to grammar 2, if you start with a subtraction, what can you put on the left and the right? Well, according to grammar 2, you can put any subtraction expression on the right of it, but you can only put a variable on the left. See how that forces you to group on the right sub-expressions. That essentially forces this guy to be grouped on the right. You can put the complicated recursive thing only on the right. On the left has to be something simple, in this case, a variable. Okay, so this grammar takes A minus B minus C. Grammar 2 forces it to be a it forces it to be the variable minus a group. It's forced to now be, by thinking recursively, we see that what this is saying is you have to have the variable minus, and then you could put the group thing, the big thing. Similarly, if this was here, so if we wanted to parse this thing, we would start off, this minus sign can't be that guy. Why not? if I'm using G2 and I have to parse this subtraction cannot be that one. Why not? What if I want to parse it that way? So I'm trying to group A and B together and trying to group C minus A minus C together. But the grammar won't let me do that. Why not?
Just an odd number of variables.
No, no, doesn't have anything to do with even or odd. If I match up this with that, right? Then I have to match this with what?
With one, you only can put one variable before the subtraction and you're putting two.
Right. See, if I make this one, I have to match him with what? So what do I have to match him with? The pattern says minus their sub-expression. So if I try to match this with this, what does this have to match to?
Var.
Var. But what does var turn into? Var matches what?
Is it A or B or A?
Yeah, A or B or, oh, actually, that should have been a C there. There's a misprint. Var matches with A or B or C. Now, that's not an A or a B or a C. That's a complicated expression. It's A minus B. So that won't match that pattern. Okay. See, these are patterns. This thing tells you how to match something. This thing tells you how to match this. Okay. If I try to match this one with this one, I can't match that with what's over here. What if I try to match this one with this one? Will that work?
No, you just have three things trying to fill the variable slot instead.
Yeah. So the only way that I can match this to this pattern is I have to put the minus sign there. Then there matches the A, and then see everything else is grouped to the right. So everything else is in the recursive part. So, okay. Now see, if I went back to this, if I went back to G1, I could do anything I want. Can I match this with that in G1? Now go back to G1. Can I match that one with that one?
No reason you couldn't.
Good, because then that's a sub-expression, subtraction expression, and that's a subtraction expression. On your hand, I could also match this one with that, because there's a subtraction expression on the left and a subtraction expression on the right. So G1 doesn't really give me any structure. G1 doesn't force a structure on me. G1 has too much recursion. It has so much recursion, it's ambiguous, because it's saying you could, a subtraction expression is a minus sign with any subtraction expression on the left and any subtraction expression on the right. So this guy can be said to be this one with that subtraction expression on the left and that on the right, or it could be this one with this subtraction expression on the left and this subtraction on the right. So it doesn't group things. It lets me group things any way I want. It doesn't group them the way I want to group them. But when I narrow down the amount of recursion in G2, see, I have less recursion in G2. I have what's called right recursion. See, over here, there's recursion on the right-hand side of the operator. So that's called right recursion. Here I have left recursion, okay? I have right recursion there. Now, when I go to match the minus sign here with the minus sign there, well, I don't have much choice about what's on the left. It's very limited. I can only have a variable on the left. So that means I can't match this minus sign, that minus sign, that minus sign. Oh, notice that you can't just say, oh, I'm gonna, like, here's one thing that at the beginning you might think. Suppose I'm gonna match this guy with that guy. So you say, fine. There is C. What's wrong with that reasoning? Okay, match this guy to that guy. Match the C to there. And match A minus C to the subtraction expression. What's wrong with that reasoning? That minus sign is that one. A minus C is this right hand. And that letter C there is there. Okay, I match things.
You still have A and B left over.
Yeah, you didn't match the whole pattern, and you have no way of going back to the A and the B, A minus B. You'll end up parsing only this piece of the string, and you'll have left this thing dangling because you'll have matched there to C, minus to minus, and subtraction expression to A minus C. So that parsed only that part, but you're not supposed to parse only a part of it. You have to come up with a way of parsing the whole thing. You can't just parse a piece of it. Okay, so you have to start at the top, at the first time you go, you have to parse the whole thing. So like this minus sign, see, when I match this minus sign with this one, I match A with there, and I match everything else with sub-expression. So I match everything. A to there, subtraction to subtraction, B minus C minus A minus C to subtraction expression. Okay, so I match this one to that, this one to that, and then this matches everything that's left. But then I have to check that it still works. Okay, so then I have to do the rest. I have to still do what's left. Okay, how am I going to do what's left? Okay, but now I go back to the recursion. This now is this blue stuff here. And I have to do my pattern match again. Can I match this minus sign with that minus sign? The answer is no, because I would be matching A minus C to the sub-expression, but I can't match all of that to just there. So you have to match all of it. The only way I can match this pattern to all of this is to match that one to the minus sign, B to there, and then that part there will be the subtraction expression on the right. Okay. Then I'm back to now parsing this. See, I'm recursing. So I'm back to this where I'm parsing this thing. Okay. So I have to parse this thing using this. And the only way to do it is, again, that guy is that subtraction, so that I have a C on the left, and then I get this on the right. So now I have to parse that one separately. Okay, notice I'm breaking off a big thing over and over again on the right because it's right recursion. So that ends up parsing this as that group that does this, that one parses things as right associative. See, what that one does is it makes this thing the first thing you would actually do. See, that would push this one lower in the tree. So if I'm using G2, I have, if I were to build a tree out of this one using G2, I would have that subtraction with A on the left, see, I had this subtraction is here with A on the left, and then all this was on the right. Then this parsed as a subtraction with B on the left and all of this on the right. Okay. Then this parsed as a subtraction with the C on the left and this on the right. Now, finally, I get down here to the first thing when I compute this, I do the subtraction of the A and the C. Okay. So this grouped it as those two first, then that subtraction, then that subtraction, then that subtraction. So it was grouped as A minus the grouping of B minus the grouping of A minus C. No, yes. Oh, minus the grouping of C minus the grouping of A minus C. Okay. This is right associative. See, I did things from right to left. That's not the way we usually do subtraction, but grammar 2 made my subtraction right associative. And right recursion gives you right associative. That's one of the most important, that's one of the grand lessons of this subject, is that right recursion in your grammar forces right associativity of your operator. Okay, because you keep peeling, you put the big stuff on the right. Every time you do a parse, the recursion lets you represent the big stuff that's left, and you have to have something small on the left. We'll see, this is going to be a pattern you use over and over again. You go from, see, this thing had too much recursion. It lets you put anything on the left and anything on the right of the subtraction. This one narrows down the recursion. You can put anything you want on the right of the subtraction, but you can only put a variable on the left. So you're forced to have a small thing minus everything that's left. So that's A minus everything that's left. So that makes the tree A minus everything that's left. So that's pushing these guys farther down the tree, and it's making it right associative. On the other hand, if we use G3, if we go to the G3 grammar with the same thing, G3, because the recursion's on the left, we have to do things differently now. I'm going to parse this thing using G3 now. Where's that minus sign? Well, for a similar reason, I can't make it that, because I can put anything I want to the left of the minus sign, but now on the right of the minus sign, I can only have a letter. So I can't have all this on the right. I could have that letter, but then I'm leaving all this stuff undone. So the only thing I could do is parse over here. I match that guy, I'm sorry, I match the subtraction to that one. That's the var, and that's the subtraction expression on the left. Okay, so now it's parsed kind of like this. That guy off to there, and I have to parse this thing now. So now this is the sub expression, and I do things recursively. Again, now, I'm sorry, I'm over here, G3. Okay, now I have to parse that using G3. That minus sign can't be put there because I can only have a variable on the right. It has to be put over here. Okay, so now that's going to be peeled off, and I'm left with that as the sub expression. Okay, so now I'm going to recurse and do this guy as a sub-expression, and I have to put this thing, match it with the sub-expression, and this thing with there. Okay, right? So now I'm left with the big thing on the left. Okay, and that forces me to parse this thing, the other associativity. Okay, so what it's saying is that I have the minus C at the end, and everything to its left is grouped together. See, the big stuff was on the left. I had a minus variable. Okay, so that was all this on the left. But on that thing, I had the A there with a subtraction and everything on its left. So that's this stuff here to the left of the A. Now that's going to get parsed with a C there and a subtraction of everything on its left. Okay, that was this. So that's left with the A minus B there. Okay, so it grouped it on. See, now this one is now left associative. This one moved from left to right. It did A minus B, then subtracted off the C, then subtracted off the A, then subtracted off the last C. Okay, left recursion gave me left associativity, because left recursion forces me to lump things on the left. Okay, so that peels off this guy first. So if I made the tree for this one, the tree for this one is a subtraction tree with something on the left and something on the right, and the thing on the right is the C by itself. And all this is on the left. What's on the left is a subtraction tree with a little hard to draw it. It's got the A on his right and a whole bunch of, and now all this on the left. Okay, now that is a subtraction tree, and it's got a C on its right. It's got a C on its right, and on its left is this stuff. So on the left of that subtraction tree is another subtraction tree, and that tree has A and B on its left and right. Okay. Notice A, B, C, A, C, A, B, C, A, C. The leaves look the same, but they're in the same order if you read from left to right, but they're grouped differently. This is the subtraction. This is that A minus all of this. Now it's A is minus only B. This A is minus only the B. We do from left to right. Yeah, from our point of view, that's the right one. The arithmetic we use is got a grammar that's left associative, left recursive. This is the right one from our point of view. Okay, but on the other hand, this is the one that would be good for equality operator. If I replace this minus sign with equality operators, then this is the right way to do it, because equality should be parsed from right to left. Equality, you do say, let A equal C, then C equals that result, then B equals that result, then A equals that result. So remember, we mentioned that in class the other day, that the equality operator is right associative, but the subtraction and addition operators are left associative. So this is the right grammar for an operator. This one's the correct grammar for an operator like equality operator. This is the correct one for an operator like addition, subtraction, multiplication, division. Okay? right? So, whoops. Let me put back the minus signs. Oh. Okay. Whenever you design a programming language, you have to decide how every operator should act. What's the reasonable way for your operators to act? Okay. Do you want your operators to act? Let's see. You think about it. Should your operators be left associative? Should they be right associative? What makes the most sense for you? Yeah. And now for arithmetic, that was decided a long time ago. But for programming like equality, you don't do this so much in arithmetic. You don't write things too often in a algebra class like x equals y equals z. You don't write that too often. But if you do, it makes sense to do it from right to left. Okay, not from left to right. But if you put subtractions in there, you're supposed to do it from left to right. Okay, right. So if we think about this from the point of view of recursion, this represents an arbitrary subtraction expression. And it's saying that an arbitrary subtraction expression is a minus sign with any subtraction expression on the left and any subtraction expression on the right. Now that means that when you go to parse something like this, you can parse it pretty much any way you want. There's a subtraction with an expression on the left, an expression on the right, but so is this. There's a subtraction with an expression on the left, an expression on the right. So you get multiple ways to parse it. If you get rid of some of the recursion, okay, but then you need another production, okay? But if you get rid of the recursion by producing another production, then you can make that production represent something simpler. So then you say a subtraction expression is something simple. And later on, we'll see that the simple thing can be, it isn't always just going to be a variable. But the idea is that you would say a subtraction expression is something simple on the left and a subtraction expression recursively on the right, or a subtraction expression on the left and something simpler on the right. By reducing the amount of recursion, you force things to parse either left associative or right associative. And right recursion gives you right associativity. Left recursion gives you left associativity. Okay? Right, so that's one idea. Okay, now the other idea is what happens when you mix up operators. When you mix up operators, associativity isn't the question. Order of operations is the question, precedence. Okay, if I say 4 minus 5 minus 6, I want to know, do I do 4 minus 5? Do I do this from left to right or right to left? Okay, but if I put a times there, it's not a matter whether I do it from left to right or right to left, because if I do this 4 minus 5 times 6, it's not a matter of left to right or right to left. It's now a matter that multiplication is done before subtraction. Multiplication is done before subtraction. So this one's going to be done right to left, and this one's going to be done left to right, because the issue is multiplication comes before subtraction. Multiplication comes before subtraction. So now it's not a left-right issue. Now it's a matter of which operator has higher precedence. Okay. Now, G4, see, it's got recursion everywhere. That's not good. See, it's got two operators, but it's got recursion everywhere. So if I create a complicated expression, 4 plus 5 times, keep hitting the wrong key. 4 plus 5 times 6 plus 4 plus 5 times 7 times 8. Okay. I can if I use G4, there's no order of operations going on here, because I could say, oh, this plus is that plus, right? And then there's a arithmetic expression on the left and an arithmetic expression on the right. On the other hand, I could make that star this star. And I can say, well, there's an arithmetic expression on the left and an arithmetic expression on the right. See, there's too much recursion there. It's saying that an expression is a sum of two expressions, or it's a product of two expressions, which is correct, but it doesn't tell me how to parse. It does tell me what I can write. This lets me write any legitimate arithmetic expression, but it won't let me parse them, or it'll let me parse them lots of ways. So it won't tell me what order to do the operations in. This grammar is not going to help me tell a programming language. It tells me how to write. It tells me what the grammar is, so I can write. It tells me what are all the legitimate arithmetic expressions. It's good for that. So you could say that this is a legitimate grammar for arithmetic. It writes all the correct expressions, but it's not useful for a programming language because it doesn't say what order you should do the operations in. Now, if we were to look at this, we would say you got to do that first, because the product has higher precedence than the addition. Now, what about this? What do you do with those? What are you supposed to do with 5 times 7 times 8? Is that correct? Can I group it like that? Should I group it like that? What's the rule when operators have the same precedence?
Would you group 5 times 7 first?
Yeah, you do it from left. You should do it from left to right. So if it looked like this with no grouping, since these are at the same precedence level, it should be grouped. Do those two first, and then do the last multiplication. All right. Now what do I do next? So that gets done. That gets done. Then that one. What operation's done next? I haven't said how to do the additions yet. There's 3 addition operators. Which one gets done first?
The far left.
The far left one. You move from left to right. So that would group this one like that. You do that addition next. And then you'd have to do that addition next. And then that leaves this one for the end. Okay, so this expression, when it's parenthesized correctly, is the one below it. In the rules of arithmetic, this means that, but we want our grammar to do that for us. Grammar G4 isn't going to do that for us. Grammar G4 is not going to give us this tree. Now, this is now a tree. That guy's at the top. That's his right branch. That's his left branch. In this right branch, that one's at the top. And then this is on the left. And on his left branch, that one, let's see, that one's at the top with a 4 on the left and all this on the right, on the 4 on the right and that on the left. So this is a tree. Okay, so there's a tree there. I'm not going to draw the tree because it'll take me a little too long, but there's a tree there. This guy's at the top of the tree. He's the last operation done. Okay. This would be at the bottom of the tree, and this would be at the bottom of the tree because they're the first operations done. Now, you actually don't know whether you do this one first or this one first because it doesn't matter. Okay. They just have to be done. This one has to be done before you could do that one. And this one has to be done before you can do that one. So you actually don't know if you should do this one first or this one first. And it doesn't matter if you do, you can even do them at the same time. In modern programming languages, that's called parallelism. You could actually literally do that multiplication at the same, if you have two cores, you could have one CPU doing that multiplication while another CPU is doing that one simultaneously. That's what modern CPUs do. They would actually do those simultaneously because it doesn't matter what order you do them in. So do them at the same time. But that one's got to be done before you can do that one. Okay. And that's got to be done before you could do that one. But you could do this one and this one at the same time. They could be done simultaneously. Okay. So that's an interesting thing that you worry about later on is if it doesn't matter what order they have to be done in, you could either do them in either order or you could do them at the same time. If it doesn't matter if you do this one first or that one first, in fact, you could actually do them in parallel simultaneously. And that's what modern parallel programming tries to do. Okay. Now, how do we get a grammar that would take this thing and make that thing out of it automatically? So the structure of the grammar, see, that one's not good enough. Okay. The grammar isn't going to help us because it's got too much recursion in it. Okay, it's got too much recursion in it. So go to G5. G5, there's less recursion in G5, but you have to look carefully to see where it is. Okay. See that there were 4 things of recursion here. You could have a plus with an expression or a product with an expression or an expression. In G5, you have a plus with an expression or expression, but then there's no, see, then it says or, then it says or, instead of there being this, it says or that. Okay, so there's less recursion going on here in some sense. You can do an addition or you could do this guy. Then this guy is multiplication. But notice that this guy is not, see how this was a product is any expression with any expression. Here's where we really restrict the recursion. A product now is a multiply expression and a multiply expression. See, we've really restricted the amount of recursion here, and that's going to help us. Okay, there's still a lot of recursion here. This is a level of recursion, but down here, if we put EXP here and EXP here, we wouldn't have changed anything. Grammar G5 would essentially be the same as G4. It would just be G4 written in a more complicated way because it would have essentially the same amount of recursion. The trick is that G5 is going to be restrictive here. Here you could say, well, what's a multiplication? It could have anything on the left and anything on the right. Now, multiplication can only have this on the left or this on the right. Now, this grammar has another step. And then what could be this thing? It could be either a parenthesized expression or the letters A, B, or C. Okay. See, this can't be any. Notice that on the left and the right of this guy can't be a sum. See, you can't get back to addition here unless you go through parentheses. Okay. It's tricky to read, but what it's saying is that a multiplication can't have addition on the right. So that's saying that if we think of it from over here, a multiplication can't have 4 plus 5 on the right. That can't be like that because that would put the 4 plus 5, that would mean that the multiplication is done after the addition. If this was lumped 4 plus 5 on the right of a multiplication, that'd be saying that the 4 plus 5 has to be done first. This grammar says that on the right of a star, you either have a parenthesized expression or the letters A, B, or C. So I could put a parenthesized 4 plus 5, but then I'm saying do 4 plus 5 first. Or I have to have something simple like a letter A here. Okay, but I can't have A plus B there. I can't have that lumped together. The grammar won't let me do that. On the right of a star has to be a multiplication expression. Now I could put another multiplication expression there. See, on the right of a star, I could have a multiplication expression. This grammar, unfortunately, leaves, suppose I do this. This grammar still has too much recursion in it because it doesn't tell me if I should do this multiplication first or I do this multiplication first. Because this grammar says what's on either side of a star? A multiplication expression and a variable, fine. But I could also say what's on either side of this star? A variable and a multiplication expression. See, on the left and right side of a star could be another multiplication expression or a group or a variable. So I still have too much ambiguity in this grammar. It's going to make multiplication have higher precedence than addition, but it won't tell me how to do the multiplications. It won't say whether to do them from left to right or right to left, because there's still too much recursion in this grammar because of that thing there. It also doesn't help with the additions. This is too much recursion on the additions. With this grammar, if I write A plus B plus C without any multiplication, just do the addition part. This grammar doesn't help me figure out how to do that. This grammar says an addition can have anything on the left and anything on the right. So that could be this addition with A on the left and addition on the right, or this one could be that addition with an addition on the left and a variable on the right. So this grammar is still not completely correct. It does make multiplication have higher precedence than addition, but it doesn't say whether addition should be done from left to right or if multiplication should be done from left to right. So it does precedence. Where we say is this grammar does precedence, but not associativity. So it's only doing one of the two. Then the grammars that come later, specifically G6 is going to be the one that does associativity and precedence by getting rid of a lot of the recursion. G6 is going to have a lot less recursion in it. We'll see in a minute. G6 has less recursion. Okay, so G5 has less recursion than G4. By having less recursion than G4, G5 does put multiplication at a higher level of precedence than addition. Okay, let's do a simple example just to check that. Let's do A plus B times C and compare it to A times B plus C. Let's see that it doesn't matter if we do it, the multiplications on the right or on the left, it's going to come first. Okay, so let's check how this grammar is going to do this. So we're going to work with G5. Okay, and we want to let's do the first one. Let's do this one. Okay, so an expression is either a sum of two things or it's a multiplication thing. Let's try to match that one with this and see if it works. Okay. All right. Now this is tricky. If I match that plus with this plus, then I have to say that this A has to match expression. Okay. All right. So now I'm starting with A with expression. Okay. An expression can be a multiplication expression, and a multiplication expression can be the letter A. Okay. So I can match A with expression. So expression is a multiplication expression, and a multiplication expression is A. So I can group the plus. So I can start here with plus and make this guy expression. Okay. Now, but what about this guy? Can I make him work? Okay, I wanted this to be a B. Okay, I'm trying to parse this way. The left side worked. B times C. Can B times C be an expression? Whoops. Can B times B be an expression? Okay. Well, then, now this is B times C. B times C can be a multiplication, and a multiplication can be something times something, and that can be in B into C. So that this will parse that way. Okay. But it pushed this guy, it made this guy the last thing done. See, we parsed it as this guy being the last thing done. So what we just did was we parsed it as a plus of A with a product of a B and a C. So we kind of did the obvious thing and it worked. Now, what if we tried to do it the wrong way? What if we tried to use G5 to do the, okay, let me just finish this. This has got a B and a C. So we parsed it that way. Okay. What if I tried to parse it the other way? What if I tried to make this guy the last operation with this on the left? Okay. So I would try to say expression, I'm in G5. And I want to say an expression is a product of two things. Okay, well, an expression can be a product. Okay. So now this star is that star. This guy can be that one. So far, so good. But that means this one has to be that one. Okay, but multiplication expression doesn't allow for a sum of two things. See, I'm not allowed to go back up to here. See, I can't go from multiplication expression to expression. I'm stuck now in a loop down here. I did multiplication of something with something. So I'm down here, multiplication of something with something. My left-hand thing is this one, but I'm stuck in this loop down here and there's no addition. And I didn't put parentheses around there, so I can't use this. I don't have a letter by itself, and I don't have another multiplication operator. So I'm stuck. I couldn't parse this as a product of C with A plus B. I couldn't group it this way. Okay, so G5 didn't let me give addition higher precedence. It forced me to give multiplication higher precedence. See, it's kind of tricky. It's amazing how this stuff works. It's yeah. The fact that anybody thought of this, I'm always struck by how this is really not trivial. It did take years for people to sort this stuff out. This was done in the 50s and 60s when programming languages were first being invented. It was in the 50s and 60s that people really started figuring this stuff out. Okay, with the languages like Fortran and Algol and languages that aren't used so much anymore. But they're the ones who figured out that this was the way to make languages work. Okay, now let's try this one down here. Okay, G5, okay, with this one. Again, G5 should force that to be done first. It should not allow us to do that first. It shouldn't allow us to parse the pluses at first. So go down here and we're going to parse with G5, okay? Suppose we try to say there's a sum, okay? There's a sum of something on the right with something on the left, okay? So there's a sum of something on the right and something on the left, okay? Does that parse? Well, the something on the right is an EXP, and we've said before, an EXP can be a multiplication expression, and a multiplication expression can be the letter C. So that C on the right works, okay? Now what about this part on the left? Okay, so that's a plus That's an EXP. But an EXP can be a multiplication expression, and a multiplication expression can be a star with something on the left and something on the right, and each of those can be a letter A and B. So it worked. It parsed as a plus of we put the star on the left and we put the C on the right, and we have the star being the multiplication of A and B. The grammar let us parse it that way. Okay. So we just said, okay, that plus is that one. Now, what if we tried to force it the other way? What if we tried to put this thing as at the top of the tree with this on its left and this on its right? Okay. So then, well, expression can be a multiplication expression, and a multiplication expression can be that star. So now we've got that star is this one. Okay. Multiplication expression on the left, and a multiplication expression on the left can be a letter. But then we get the same problem now. The multiplication expression on the right is trying to be that, and that guy can't be a multiplication expression. We're not allowed to go back up to the top and go up here because we're down here under multiplication expression, and we don't recurse back. I'm sorry, we don't recurse back up to here unless we put parentheses around it. See, the only way to recurse back up to here is that we have parentheses around the thing that recurses. If we don't have parentheses, and there's none here, then I can't take this guy, I can't take this guy, which is trying to be this right-hand side here. I can't take this right-hand side and go back up here with it. It won't parse now because it's stuck down here. So this grammar G5 made multiplication higher precedence than addition. But if I put a couple additions in there or a couple multiplications in there, then it won't determine the associativity. Okay, it won't do associativity. So if I do A plus B plus C times D, if I use G5, there's more than one way to parse this, but they'll always make the multiplication done first. They'll force the multiplication to be done first, but it won't tell me what order these additions are done in. This grammar G5 won't tell me what order to do these additions in. So I could parse it as this sum of that product with that on the left, or I could parse it as this sum with that sum on the right, and then that sum has that on its right. I'll always have this product being done first, but I could have either this addition done last, or I could have this addition done last. This grammar, because it's got too much recursion right there. Too much recursion right there. Similarly, if I did A plus B times C times D, G5 would force me to do these multiplications before the addition. Like I wouldn't be able to do this as A plus B first. No way. G5 won't let me do the A plus B first. It'll force the multiplications to be first, but it won't force me to do that multiplication first or that multiplication first. G5's got too much recursion right there. So it doesn't say how associative the multiplication is. So I could either do that multiplication first, followed by that one, or I could do that multiplication first, followed by that one. But I have to do all the multiplications before I can do the addition. So G5 will give me the right precedence, but it won't give me the right associativity. Okay. Now, G5 prime is interesting because what if you have multiplication and exponentiation? That means powers. So this is a common symbol. C and C++ and Java don't use this, but a lot of languages do. That means A to the power B. Okay, so this would be 2 cubed. Double star for exponentiation is a fairly common thing. Fortran uses that, MATLAB uses it, a lot of other languages use it. Some languages use caret to mean raised to a power, and some languages use that. Does anybody remember, how does C and Java and C++ do exponentiation? What if I want to do
I
2
think
cubed?
Java doesn't have it.
How do you, but I mean, I can compute 2 cubed in Java. How do I do it?
Math.pow?
Pardon me?
Math.pow?
Yeah, you have to use a library function. Instead of it being an operator, it's a function. Instead of it being an operator, the Java language did a function, math.power 2, 3. This is an important design. Do you want an operator or do you want a function? Some languages want an operator, some languages want a function. I'll give you an example. Not every language has a plus operator. There are a few languages out there that make you do add 4 and 5. They don't have operators. There are some odd languages out there that don't have operators. They only have functions. Java takes the point of view that exponentiation should be a function, not an operator. Fortran and MATLAB make exponentiation an operator. So exponentiation is kind of quirky. There's good reasons to make it a function instead of an operator, and there's good reasons to make it an operator instead of a function. Addition, almost everybody makes it an operator, but some languages make it a function. You use function notation, not operator notation. Okay, so Java and C don't have the exponentiation operator. They have the power function, and they don't call it EXP. They do have an EXP function, but that's specifically the e to the power function. That is e to the power x. So that's the e exponentiation function. Okay, so the base is e. The EXP function has the base e. If you want the arbitrary power function, like 2 cubed, that's they call it the power function. So
Is it a
another way to
function
put it,
because
say what?
is it a function because most hardware doesn't have they don't have an opcode for
No,
X?
no, that's not why. No, that's not the reason why. That wouldn't matter to them at all. They don't care whether the hardware has an opcode for exponentiation or not. That's not the reason why, because they could just as easily compile this function to that opcode or not. They could just as easily compile this operator to the opcode or not. No, it's got to do with, I'll show you what it's got to do with. I'm going to use this to mean exponentiation. What's that mean? What's going on here? What's going on here?
Would it be 2 to the power of? Would it be the third one?
Well, okay, what's going on here? What am I pointing out?
It's not obvious which one to use without the parentheses.
Right. Should I group it left or should I group it right? Now, the problem is no one has ever said for the exponential no one has ever said in the world which one of these is right. TI calculators do it one way, HP calculators do it another way, MATLAB does it one way, Fortran does it another way. There is no agreement out there where the exponentiation operator groups on the left or groups on the right. There's never been an agreement about that, all right? So this is ambiguous. A TI calculator does it one way, an HP calculator does it another way, Fortran does it another way, okay? So here's why MATC does functions. Now, 2. By doing it with functions, you have to group it. Let's see, what's the other grouping? Oh. You have to group it. So they don't have an ambiguous syntax. That's the advantage to function calls. Function calls force you to group things. So the designers of the C language did not want something ambiguous in their language. They did not want somebody typing that and half the world thinking it meant this and half the world thinking it meant that. You know, they would have to pick which one it meant. It had to mean either this, or they would have to have this not compile. Yeah. Or they would do a thing where this would be non-associative and it wouldn't compile. So they either have to have this thing not compile, or they would have to choose one or the other. By using functions, you have to do the grouping. This one is the power 2 to the 3 to the 4th power. This is 2 to the 3rd power raised to the 4th. So this one groups it like that. And this one groups it like that. So they chose function notation so that you would have to group it yourself. Okay, that was a reasonable strategy to get rid of this ambiguity. Okay, the other choice was just to make this not compile, or if they were using the double star, they would have to make that not compile. But that's not such a great thing either. Okay. All right, so we'll finish this. Okay, now, so what we're going to do is, this language gives you exponentiation and multiplication. And see, by pushing things down lower, by having multiple grouping, this gives this higher precedence than this. So this has higher precedence than that. Like this has higher precedence than that. Now this has higher precedence than this, which has higher precedence than that. You force by grouping, by using these symbols. A multiplication group includes a power group. Then a power group either includes a parentheses or letters. You force the grouping farther and farther down towards this operator. Okay, so you can have multiple levels of precedence this way. Then what we'll do on finish this is we'll see that by restricting the recursion more, you can put back the associativity. G6 puts back associativity, left associativity, because no, actually they put right associativity. I think he goofed up. I have to look. He put no, I'm sorry. There's left recursion, so it's left associative. See, there's the left recursion, that's left associative. There's the left recursion, so that's left associative. And then this is not recursive. It forces you to go down. Okay, and then this is not recursive. It forces you to go down a level. So it's G5 with less recursion, so that puts back the associativity. Okay, and this is not trivial. This is really tricky stuff, but it's how programming languages work. It's how programming languages let you type these expressions, and then the programming language automatically builds the right tree. The programming language will build the right tree because the programming language uses this grammar, and the grammar directs how the tree should be built. And then once the tree is built, the order of operations is correct. The order of operations is in the tree, not really in here. You have to turn this into that tree to get the right order of operations. If you turn it into a different tree, you get a different order of operations. What tree it turns into is determined by the grammar. And the grammar, it's the recursion in the grammar that really tells you how things are being built. That's the fascinating thing. It's where the recursion is that determines how the tree is built. Okay, so we should quit there. Run out of time. Okay, I'll put these examples up on the course website, and you should we'll do practice. We'll practice these two, do examples where if somebody gives you an expression in a grammar, you should be able to figure out what the tree looks like. That's what you should be able to do. If you're given an expression and a grammar, you should be able to figure out what the tree looks like. Okay. That's the kind of thing that a programmer should be able to do. Writing grammars is hard. Very few people are asked to write grammars. Very rarely are people asked to write grammars. But if somebody gives you an expression, you have to figure out what does it mean given this grammar. That's real common. And you see, JSON has a grammar, SQL has a grammar. And if you need to know what these expressions really do, it's real common to have to turn to the grammar to find out exactly what's going on. So given an expression and given a grammar, you should be able to figure out what the tree is. All right. What you're not supposed to be able to, like at this level, I wouldn't say write me a grammar. That's too hard. Writing a grammar is tricky. But reading a grammar is what you should need to do. And you read a grammar by saying how it tells you to build a tree. Given an expression, so given an expression and a grammar, build the tree that the grammar directs you to. Unless the grammar is ambiguous, in which case it could let you build more than one tree. Okay, so we'll quit there. If you have any questions, I have office hours after class, and if you have questions, you can send me an email. And then we'll meet on Tuesday. We'll do a couple more examples of seeing exactly why, in this case, why this one works, why the reduction in the recursion ends up giving us the right grammar for arithmetic. There's the grammar for arithmetic. Well, and then we'll start looking at ML, the functional programming language ML. Okay. All right. So any last question? Anybody have any last question? Okay. I'll stop sharing and we'll have a nice weekend. See you next week. Bye.